Welcome to Azure Simplified. Here we are going to learn about high availability and disaster recovery strategies. Table of contents. Introduction. Understanding recovery objectives. Recovery time objective, RTO. Recovery point objective, RPO. High availability and disaster recovery, HADR, options. Overview of HADR strategies. Azure HADR features for virtual machines. Built-in availability and recovery features. Best practices for Azure VMs. HADR for PaaS deployments. Challenges and solutions. Key Azure PaaS HADR services. IaaS-based HADR solutions. Designing a resilient IaaS HADR architecture. Implementation best practices. Hybrid solutions for HADR. Integrating on-premises and Azure. Networking considerations. 1. Describe recovery time objective and recovery point objective. Recovery time objective, RTO, and recovery point objective, RPO, are key metrics in high availability and disaster recovery, HADR, planning. They define acceptable downtime and data loss, shaping the architecture and response strategy for business continuity. 2. Recovery time objective, RTO. RTO refers to the maximum time allowed to restore resources after an outage. If exceeded, consequences may include financial losses, work disruption, and penalties. RTO applies at both solution and component levels, e.g., SQL Server instances, databases. The overall RTO is determined by the slowest component in the recovery process. 3. Recovery point objective, RPO. RPO defines the maximum tolerable data loss in case of failure. Example: if RPO is 15 minutes, data should be restorable up to 15 minutes before the failure. Backup strategies must align with RPO to ensure data is recoverable within the acceptable loss limit. Defining RTO and AMP, RPO. Business impact analysis helps determine RTO and RPO based on downtime costs. RTO and RPO influence both the technical architecture and operational policies. Example: if downtime costs $10,000 per hour, investment in solutions should align with this impact. Testing backups and failover mechanisms is critical to ensure RTO and RPO are achievable. High availability, HA, vs disaster recovery, DR, considerations. HA, high availability, addresses local failures, enabling rapid failovers within a data center, e.g., always-on availability groups. DR, disaster recovery, involves full system recovery from a major failure, often requiring longer recovery times. RTO and RPO for HA and DR should be separately defined as recovery efforts vary in complex documentation and review. RTOs and RPOs must be formally documented and periodically updated. Once established, technology solutions, e.g., failover cluster instances, backup strategies, should be selected to meet the defined objectives. If expectations are unrealistic, adjustments to RTO and RPO are necessary to align with real-world constraints. IaaS versus PaaS for availability. IaaS, infrastructure as a service, full control over SQL Server and high availability and disaster recovery solutions. PaaS, platform as a service, built-in high availability and disaster recovery with minimal configuration. The choice between IaaS and AMP, PaaS impacts HADR design. SQL Server HADR features for Azure Virtual Machines. Always-on failover cluster instance, FCI, protects entire SQL Server instance. Always-on availability group, AG, protects individual databases. Log shipping, simple backup-based, DR, method. Always-on failover cluster instances, FCI. An FCI is a configuration that is assigned a unique name and IP address, different from the underlying cluster nodes. This allows applications and end users to access the FCI without knowing its location. Azure-based FCIs require an internal load balancer, ILB, to ensure connection. When an FCI fails over to another node, the entire instance restarts on another node, disconnecting any connected applications. The instance then goes through a recovery process, ensuring consistency to the point of failure. FCIs require shared storage to ensure another node can access the database. Always-on availability groups, AGs, in SQL Server. AGs provide database-level protection, with a primary replica containing read, write databases and a secondary replica for transaction synchronization. AGs provide abstraction with a listener, similar to an FCI, with its own unique name and IP address. AGs can have a quicker failover time than FCEs, but they require more storage due to each replica having a copy of the data. Any object outside of the database or not captured in the transaction log must be manually created and accounted for on any other SQL Server instance. The comparison between always-on failover cluster instances, FCI, and always-on availability groups, AG, highlights key differences in their functionality and requirements. Scope of protection. FCI provides instance-level protection, meaning the entire SQL Server instance is covered, while AG protects individual databases. Failover process. FCI requires a full stop and restart of SQL Server, which may cause downtime, whereas AG has a faster failover with minimal disruption. Overall, FCI is suited for organizations needing full instance-level protection, whereas AG offers more flexibility, faster failovers, and better scalability for high availability at the database level. Log shipping in SQL Server. Log shipping is a simple high availability and disaster recovery (HADR) solution for SQL Server. Primarily used for disaster recovery, but it can also enhance local availability. Provides database level protection, requiring manual handling of SQL Server agent jobs, linked servers, and instance level logins. No native abstraction, so failover requires handling name changes manually. The process involves full backup of the source database on the primary server, restoration of the backup on a secondary server, transaction log backups from the primary database, and restoration on the secondary server to keep it synchronized. Azure Availability Sets. Availability sets provide uptime against Azure-related maintenance and single points of failure in a single data center. They are separated into fault domains and update domains to support updates to the underlying Azure infrastructure. Fault domains are sets of servers within a data center that use the same power source and network. Update domains indicate groups of virtual machines and underlying physical hardware that can be rebooted simultaneously. Availability sets and zones don't protect against in-guest failures, hence additional solutions like AGs or FCIs are needed. For a multi-tier application, each tier should be placed into its own availability set. Azure Availability Zones. Azure regions consist of multiple data centers with low latency network connections. Resources can be deployed into Zone 1, 2, or 3. Zone numbers are logical representations of physical locations within an Azure region. Zone deployments may introduce additional latency due to distance. Azure Site Recovery. Azure Site Recovery provides enhanced availability for VMs at the Azure level and can work with VMs hosting SQL Server. Azure Site Recovery replicates a VM from one Azure region to another to create a disaster recovery solution for that VM. Azure PaaS Availability and Models. Azure SQL Database and Azure SQL Database Managed Instance offer active geo-replication and auto-failover groups. Azure Database for MySQL has a service-level agreement ensuring 99.99 availability, ensuring minimal downtime. Retry logic is required for applications to handle transient failures. Azure Database for PostgreSQL uses a similar model to MySQL, but also offers C2s, a scale-out hyperscale solution. Standby replicas are configured for every node of a server group, doubling the number of servers. Both Azure Database for MySQL and PostgreSQL support a read replica, enhancing availability by existing in another region. This diagram represents a high availability setup in a virtual network using Windows Server Failover Cluster, WSFC, with always-on availability groups in an Azure environment. Here's a breakdown of the components. 1. Virtual network. The entire setup is contained within a single virtual network in Azure. It consists of two subnets, Subnet 1 and Subnet 2, for better availability and segmentation. 2. Domain controllers, Subnet 1. These are Active Directory domain controllers responsible for authentication and managing the Windows environment. They are in an availability set, ensuring high availability by distributing instances across different fault and update domains. 3. SQL Server Failover Cluster, Subnet 2, Windows Server Failover Cluster, WSFC. This is a cluster setup ensuring high availability for SQL Server. Always-on Availability Group provides database-level high availability and disaster recovery. SQL 1 and SQL 2, these are SQL Server nodes participating in the availability group. FSW, File Share Witness, a quorum witness to help in cluster decision-making and prevent split-brain scenarios. 4. Internal Load Balancer, ILB. The ILB manages traffic between domain controllers, DC1 and DC2, and the SQL Server cluster. It ensures traffic is routed correctly to the active SQL Server node. 5. Availability Sets. Both domain controllers and SQL cluster nodes are placed in separate availability sets to improve fault tolerance and reduce downtime. Purpose of this architecture ensures high availability and fault tolerance for SQL Server workloads in Azure. Allows automatic failover in case of server failure. Uses always-on availability groups for database replication and failover. This diagram represents a SQL Server Failover Cluster instance, FCI, on Azure virtual machines using Storage Spaces Direct, S2D, for high availability. Here's a breakdown of the key components. 1. Availability set. The Azure Virtual Machines, VMs, are placed in an availability set to ensure high availability and fault tolerance. This prevents downtime by distributing VMs across different fault and update domains in Azure. 2. The Azure Load Balancer, ALB, manages traffic between the SQL Server failover cluster nodes. It ensures that clients connect to the active SQL Server node in the failover cluster. 3. SQL Server Failover Cluster Instance, FCI, provides high availability by allowing automatic failover between the clustered nodes. Unlike always-on availability groups, FCI requires shared storage for data consistency across nodes. 4. Windows Server Failover Cluster WSFC is the clustering technology that ensures high availability for SQL Server. It manages failover between the VMs in case one of them goes down. 5. Storage Spaces Direct, S2D, is a software-defined storage solution that enables the use of local disks on each VM instead of shared storage, which is typically required for traditional FCI setups. It provides a shared storage experience by pooling together local disks from multiple VMs. 6. Azure Virtual Machines, VMs. There are 2 Azure VMs, each with multiple data disks. These VMs act as SQL Server nodes participating in the failover cluster. Key benefits of this architecture. High availability ensures SQL Server remains available even if one VM fails. Resilient storage uses Storage Spaces Direct, S2D, to provide shared storage without requiring a dedicated SAN. Load balancing. The Azure Load Balancer directs client connections to the active SQL Server node. Cost efficiency uses Azure VMs and S2D instead of expensive on-premises storage solutions. Use case. This architecture is suitable for enterprises needing high availability SQL Server deployments in Azure IaaS, infrastructure as a service, while utilizing SQL Server Failover Cluster Instances, FCI. This diagram represents a SQL Server always-on availability group, AG, deployment across multiple data centers, utilizing Windows Server Failover Clustering, WSFC, for high availability and disaster recovery. Explanation of components. Data centers. The setup spans 2 separate data centers, Data Center 1 and Data Center 2. This provides geo-redundancy, ensuring business continuity in case of a failure in one data center. Windows Server Failover Cluster, WSFC. The SQL servers are part of a WSFC, which manages failover at the cluster level. WSFC ensures that if the primary SQL server fails, one of the secondary SQL servers takes over. Primary and secondary replicas. Primary replica, active node. The primary SQL Server instance in Data Center 1 handles all read and write operations. Secondary replicas, passive nodes. There are 3 secondary replicas, 1 in Data Center 1 and 2 in Data Center 2. These secondary replicas receive continuous data replication from the primary instance. Green arrows, data replication paths. The green arrows indicate the data replication flow from the primary instance in Data Center 1 to the secondary replicas, 1 in Data Center 1 and 2 in Data Center 2. This replication can be either synchronous, for high availability, or asynchronous, for disaster recovery. High availability and disaster recovery, HADR, features. Automatic failover. If the primary node fails, WSFC will automatically promote one of the secondary replicas to primary. Geo-redundancy. Data Center 2 acts as a backup location in case Data Center 1 becomes unavailable. Load balancing. The secondary replicas in Data Center 2 may also serve read-only workloads. Key benefits of this architecture. High availability. If the primary instance fails, an automatic failover ensures business continuity. Disaster recovery. A secondary replica in a different data center ensures resilience against regional failures. Read scalability. Secondary replicas can serve read-only queries to offload read-intensive workloads. This architecture is commonly used in mission-critical SQL Server deployments where uptime and data integrity are essential. This diagram represents a distributed availability group architecture in SQL Server. It shows 2 separate Windows Server failover clusters, WSFCs, each containing a SQL Server always-on availability group, AG. A distributed AG is used to replicate data between these clusters for higher availability and disaster recovery. Components of the diagram. WSFC1, primary AG, primary and secondary replicas. The first availability group, AG1, has primary replica, the main SQL Server instance where read and write operations happen. Secondary replica, a synchronized copy of the primary replica, ready to take over in case the primary fails. WSFC2, secondary AG, forwarder and secondary replicas. The second availability group, AG2, includes forwarder replica, a special role in a distributed AG that acts as an intermediary, receiving updates from AG1 primary and sending them to additional secondary replicas. Secondary replica, another copy of the database that can be used for disaster recovery or read scaling. Distributed availability group, red arrow. The red arrow between the primary replica in AG1, WSFC1, and the forwarder in AG2 represents the data replication path for the distributed availability group. The forwarder in AG2 is responsible for forwarding transactions from AG1's primary replica to the secondary replica in AG2. Why use a distributed AG? Disaster recovery across data centers. If WSFC1 fails, WSFC2 can take over. Improved read scaling. The secondary AG replicas can handle read workloads for reporting purposes. No shared infrastructure dependency. Unlike a traditional AG, a distributed AG does not rely on shared WSFC nodes, reducing single points of failure. Easier data migration and upgrades. You can use the distributed AG to migrate databases from one data center to another with minimal downtime. This architecture is ideal for organizations requiring high availability across multiple locations for disaster recovery and business continuity. This diagram represents a backup and restore process in a server environment, involving a primary server instance, secondary server instances, and a monitoring server. Key components. Primary server instance. This is the main server that initiates the backup process. A backup job, 1, is executed, creating a backup of data. The backup is stored in a backup share, a storage location accessible to other servers. Backup share. This is a centralized storage location where the backup data is kept. Other servers can access this location to copy and restore data. Copy jobs, 2. Secondary servers retrieve backup data from the backup share using copy jobs. These jobs transfer the backed up data to the respective secondary server instances. Restore jobs, 3. Once the copied data is available on the secondary servers, restore jobs are executed. This step restores the data to operational status on the secondary servers. Secondary server instances. These are additional servers that receive and restore the backed up data. They ensure redundancy and availability in case of failure in the primary server. Monitor server instance. This server tracks the backup and restore operations. It collects status and history information from all involved servers. Ensures that backup processes are completed successfully. Overall process, the primary server creates a backup and saves it to the backup share. Secondary servers copy the backup from the backup share. Each secondary server restores the copied data to be operational. A monitoring server tracks the entire process and logs status, history. This setup ensures data redundancy, fault tolerance, and disaster recovery, which are essential for IT infrastructure reliability. This image shows the disaster recovery setup for an Azure Virtual Machine, VM, using Azure Site Recovery. It helps users set up VM replication to another region. Ensures that in case of an outage, the VM can be restored quickly. Allows users to conduct disaster recovery drills to verify compliance and recovery readiness. How it works. Select disaster recovery from the VM settings. Choose a target region for replication. Configure advanced settings if needed. Click Review plus Start Replication to begin the process. This setup ensures that critical applications remain available even during unexpected failures, enhancing business continuity. Hybrid solutions. Many organizations require architecture spanning on-premises and Azure or even other cloud providers. These are typically infrastructure as a service based, as platform as a service solutions don't support traditional hybrid setups. Common uses of hybrid solution. Migrating to Azure, implementing a hybrid solution to ensure a smooth and secure transition from on-premises infrastructure to Azure. Creating disaster recovery solutions, example, adding a secondary replica to Azure for an on-premises system. Azure can also act as a destination for database backups or for cold, archival storage of data.